Welcome back to Applied Algebra and Trigonometry. Today we're going to be talking about roots and radicals. You're all familiar with the term square root. Now I'd like to introduce you to the principal square root. The principal square root of a number, any number, a, say, is positive if the a is positive. In other words, if a is greater than 0, then the square root of a is greater than 0. If you are presenting a problem to someone and you want them to find both the positive and the negative square roots of a number, you must say so by using this symbolism. Plus or minus square root of 144 equals positive 12 and negative 12. Please note that what we're talking about here is what is written on the page or what you present to someone and say, here, please take this square root. If you want positive and negative, you need to indicate it in that case. Please be aware that we're only talking about setting up a problem to communicate with. When you take a square root to solve a problem, you must always consider the positive and negative square roots as possible solutions. For example, x squared equals 36. To solve this problem, you have to take the square root of both sides, which gives you x equals plus or minus 6. In the original problem, there were no radicals. I used those radicals. I took the square root as part of my solution. Therefore, I have to consider positive and negative cases. Now, with some application problems, the negative will make no sense, and at this point, you can discard the negative. But you must always consider it as a possible solution when you're solving a problem. Another term we will be talking about is the principal nth root of a number, and it is written and read as the nth root of a. You still have the radical sign, but now you have some number here, which looks a lot different, well, a little bit different, than a square root does. The thing is, that square root could have been written like this. For instance, the square root of 4. Okay, I did not say plus or minus, so the answer is 2. That is the principal square root of a number. If I ask you for the principal cubed root of 8, well, what's 8 equal to? It's equal to 2 times 2 times 2. So the cubed root of 8 would be 2 because it shows up 3 times as a factor. That's all well and good, but what if you have a negative number? What if you have, say, negative 4, and you want to take a square root of that? 4 is a perfect square, right? So 2 times 2 would give us, that would give us a positive 4. What about negative 2 times negative 2? What would that give us? Well, that would give us a positive 4. In fact, there is no real number that you can square and get a negative result. So square root of negative will always be imaginary. We're not going to be dealing with imaginary numbers now. We'll do that later. However, there is a cubed root of a negative 8, because negative 8 can be rewritten as negative 2 times negative 2, which will give you a positive 4, times negative 2, which gives you that negative 8. And how many times does negative 2 show up? 3 times. So we can pull that negative 2 right out. The cubed root of negative 8 is negative 2. Negative numbers are a little odd. They have odd roots, or rather they can have odd roots. Negative numbers do not have real even roots. Okay, one more thing I want you to remember. If a and b are real numbers and a is greater than 0 and b is greater than 0, in other words, if a and b are real and positive, then this is true. The square root of a times b equals the square root of a times the square root of b. The square root of 4 times 9 is equal to the square root of 4 times the square root of 9. Are we sure about that? Well, that would mean then that square root of 4 is 2, and the square root of 9 is 3, so that would give us 6. Is that true? Let's check it by working this way. Square root of 4 times 9 is also the square root of 36, the answer to which is 6. Was there a plus or minus in front of the radical when I started? Nope. So I'm only going to consider the positive case here. And as you can see, it's equal. The rule holds because we had real numbers that were positive and multiplied underneath the radical. Let's work on another example. How about the square root of 75? Because this is the way you will usually find your problems laid out. Usually they will not already be in a factored form. Let's see, what are the factors of 75? Well, there's 25, and that goes in there 3 times, right? Okay, according to this rule, A and B are real numbers. We can separate this into the square root of 25 times the square root of 3. They are positive real numbers. And that's, I'm going to move down now, that's going to give us 5 square root of 3, meaning 5 times the square root of 3. Let me box my answer. Let's go for a more difficult problem. Let's try this. We'll call this actual example number 1. How about square root of 400? Well, what factors are there of 400? You could factor 400 into 4 times 100, both of which happen to be perfect squares. So this will give us square root of 4 times square root of 100, or 2 times 10, 20. Let's check that. Is 20 times 20, or 20 squared, equal to 400? Yes. Now, what would have happened if you had factored this a different way, if 4 times 100 didn't immediately pop to mind? Well, here's something you can do. Go ahead and make a factor tree and start factoring. Let's say for some reason I went with 10 first. So 10 times 40. Neither one of those are perfect squares. So let's continue to factor. 2 times 5 will give us 10. Those are both primes, so I'm done with those branches. Here I have 5 times 8. It's another prime, but I have to keep factoring 8. Okay, so now I have all primes at the tips of my branches, and I could write the results of my factor tree under the radical, listing each a prime factor that shows up. But look at this. I have a pair of 2's, and I have a pair of 2's, which I can indicate here. But also, well, for one thing, I have a pair of 5's also. So there's a pair here. But don't I have a pair of pairs of 2? I do. Now let's hold on to that for just a minute. First, I'm going to write this the way I would write it if I was just looking at bringing this pair of 2's out. So the square root of 2 times 2 is 2. The square root of this 2 times 2 is 2, and they are multiplied. And the square root of 5 times 5 is 5. And nothing's left underneath the radical sign, so I have 4 times 5 equals 20. So 20, once again, is proven to be the square root of 400. Okay, let me go back and pick up that pair of pairs and see how that would make your process different. This pair of factors here is 4, and this pair of factors multiplies to be 4. So I have a pair of 4's, which I can bring out. So this will equal 4, and I have a pair of 5's. I can bring out. The square root of 5 times 5 is 5. So my answer is still 20. So you can always do a factor tree if you want. Many times they will not be necessary. So without a factor tree, what I will do is look at square root of 48. And looking at 48 specifically, find a perfect square within 48. A rather obvious one is 4, because 4 times 12 will give me 48. So let's work through this using that right now, and then I'll show you another way you could do it. So square root of 4 times square root of 12 will give me 2 square root of 12, but wait a minute, isn't there a perfect square within 12? As a matter of fact, there is. We have the square root of 4 times 3, or 2 times the square root of 4 times the square root of 3 equals 2 times 2 square root of 3. I'm just putting in every single step. All of these steps are not necessary, however, always show me some work, especially during tests. Okay, so I did all that work. Let's do this a slightly different way, because maybe when I look at 48, I remember that 16 is a factor of 48, and that is a perfect square, 16 times 3. And let's see, that means I could rewrite it this way. And then square root of 16 is 4, square root of 3. And there, I got there even quicker. And in fact, if I used slightly different notation, I could have done this, or condensed my steps a little more. As a note, do not do this on a test. I need to see at least this step. Yep, I'm not going for YouTube stardom. I am talking directly to my class. That's you. By the way, if you haven't memorized your perfect squares up through 12 squared, and your cubes up through about 5 cubed at least, now would be a good time to do that. It will make what we're doing for the rest of the semester much easier. Okay, but no, I do not have the cubed root of 375 memorized. And at this point, I'm not exactly sure what the largest cube is in there, although as I'm looking at it, I'm suspecting it's going to be a 5. But here's how I can figure out what cubes are within 375. Once again, I'm going to factor. It ends in a 5, so I know 5 is a factor, and 5 times 75 will give me 375. I can take another 5 out of there. 5 times 15, okay? And 15 becomes 5 times 3. So now I have 375, and it equals 5 times 5 times 5 times 3. And if I want the cubed root, now I'm no longer going to be pulling out squares. I'm going to be pulling out cubes from underneath that radical. So there are 3. That's 5 cubed. I'm going to bring out a 5. But there's only one 3. So it has to, oh, and remember you're cubed. It has to stay underneath that radical. So the cubed root of 375 equals 5 cubed root of 3. Do not drop the index, which is what this is called, the index of the radical, as you're working through the problem. And if on a test you showed me all of this work and then wrote this and put a box around it, I'd be good with that. Let's work the other way. What does the square root of 16 times the square root of 9 equal? Remember, I gave you this rule. And whenever you have an equal sign, the statement is true no matter which way you read it. So if you have a greater than 0 and b greater than 0, and they are both real, then the square root of a times the square root of b equals the square root of a times b. So this should equal the square root of 144. Let's check to make sure that's true. So working down this way and working down this way, I'm going to say the square root of 16 is 4, square root of 9 is 3, and that's equal to 12. And the square root of 144 is 12. So yes, that is true. But be careful. Let's look at the square root of 16 plus the square root of 9. Does that equal the square root of 16 plus 9? All of that under the radical? Well, let's see. On the left-hand side, this would give us 4 plus 3, or 7. And here under the radical, we would have the square root of 25, which is 5. So no, those are not equal. So if you are given an example like this, do not try to find the square root of 25 and add it to the square root of 144. What you must do first is PEMDAS. You have understood parentheses here, so add that together first. 169 is what you get, and the square root of 169 is 13. Let's keep these nearby, but we're going to move on to another concept, and that is if you take the nth root of some number and you raise it to the nth power, you'll get whatever the radicand is. So there's a new term for you, radicand, the expression under the radical sign. So if we have the square root of 7 squared, remembering that there's an understood index, there's another term, index, of 2, then that is equal to 7. Likewise, if we have the fifth root of negative 32 to the fifth, we would have negative 32. Really? Are we sure? Let's check this one out. Well, the fifth root of negative 32 is negative 2. So negative 2 to the fifth would give us negative 2 times itself 5 times, which would look like this. And it is equal to negative 32. Time for a challenge. Okay, 2 times the fifth root of negative 243, all divided by negative 3 times the square root of 144. Oh, well, I know what the square root of 144 is. Let me do that one first. 2 is the fifth root of negative 243. Okay, that's an odd index, so it'll work with a negative radicand. And I can say, well, 144, the square root of that is 12. But this 243, I'm going to have to do a factor tree for. So what is this divisible by? It's not even, so 2 won't work. What about 3? Remember the rule for divisibility by 3? Add the digits. 6, 9, if that's divisible by 3, then this whole thing's divisible by 3, so I'm going to take a 3 out. All right. In fact, wait a minute. That's a 9 when I add them, and 9 is divisible by 9, so I can go even bigger here. Instead of a 3, I know that 9 is a factor. So 9 goes in there 27 times. Okay, and what are the factors of 9? Because those aren't primes. 3 times 3, and 27 is 3 times 9, and factors of 9 are 3 and 3. And look at what has happened. How many 3's do I have? 1, 2, 3, 4, 5. So actually, 243 could be rewritten as 3 to the fifth. We are looking for negative 243, though. If we multiply negative 3 times itself 5 times, will we get 243? You can check it if you want, but the answer is yes. Therefore, if we take the fifth root of negative 243, we'll be taking the fifth root of negative 3 to the fifth, and that will give us negative 3. Okay, so 2 times negative 3 over negative 3 times 12. Or we could use our parentheses down here too to indicate multiplication. And now we have some common factors. So those are equivalent to 1, right? Negative 3 divided by negative 3. Okay, we can think of it as I canceled here. Negative 3 divided by negative 3 is 1, and same in the denominator. 2 goes in here once, 2 goes in here 6 times. So our answer is 1/6. Now this is an interesting line in my solution process. It should look slightly familiar, but just a little bit different. Let's move things around just a little bit and then compare it to the equation I gave you earlier. The difference between this rule and this example is that our power is under the radical for this problem, but it's outside the radical here. So that brings up, let's add this to our rule, our equation up here. The nth root of a number raised to the nth power is also equal to a. I have one final thing for you to remember. If a problem has lots of negatives in it, just take your time. Eat the elephant one bite at a time. So negative 32 is the same as negative 2 to the fifth. That looks like what we have here. Do not drop that negative though. So we have a negative, and what's the radicand? Negative 2. A negative times a negative gives you a positive 2. Today I've given you an introduction into radicals. We will use all of the concepts we've covered today at some point in the course, but for the next few days, these are the three that I really want you to remember. The principal square root of a number a is positive if a is positive, and to indicate both the positive and the negative square roots of the number. In other words, you don't want the principal square root, but you want all square roots. You have to say so by putting in a plus or minus in front of your radical. And then if a and b are real numbers and they are positive, both of them, then it is true that the square root of ab equals the square root of a times the square root of b. Remember these things as we move on.